This is a setup for a linear model. Again, that's a linear model with x, the original x value, and log of our y value. Okay, so if we have an exponential model, a truly exponential model of the form y equals a times b to the x, by graphing the x value, or the x values with log of our y values, we should get a truly linear model. So I'll put that right here. This is going to be log base 10 of those y values. So equals log, we're going to choose log base 10, the common logarithm, just because that's what we'll use most likely, or most often I should say. So log base 10 of this cell, the y value right next to it. Hit the go button and drag that on down. Okay. So what we want to do is find a linear model, or y equals a plus x times b, for our shifted x values and our log of the y values. So we're going to come up with another scatter plot. I don't know what this is. If you click far away from any of the values, it'll come up with a blank scatter plot, which can make things a lot easier. You're not having to delete anything. It's not assuming any values. So this is going to be my x versus log 10 of y chart, where my x values are those shifted x values and my y values are the log of those y values. Hit the go button and we get what looks like a fairly decent line. Again, if we have a truly exponential original model, then by graphing x and log y, we'll have a truly linear model down here. Of course, it's not truly linear. We've got some variation on top and bottom, but we get a pretty good idea for what it looks like. Now I'm going to add a trend line and use linear trend line. Use this trend line to get us going and finding the exponential model. Okay, so we'll use these as starting values for the exponential model, and then we'll adjust things like we did with the linear model. We'll adjust the a and b values accordingly. So what we've got here with the x versus log y graph, we've got a line that models y equals a plus x times b, where these big A and big B values are 2.0015 and 0.0168 respectively. So I'll type these in here. Move this over a little bit. So big A is the y-intercept, that's 2.0015, and big B is the slope, or 0.0168. Then to transform, to go from big A back to little a, we have to use a little bit of algebra. Break the pen out again here. So we've got basically log of little a. Whoa. Well, let's try this. Move this out of the way. And erase a little bit. So we've got log of little a is equal to big A right here, but big A is equal to 2.0015. To undo the common logarithm, we're going to raise both sides to be exponents with base 10. So this is 10 to the log little a is equal to 10 to the 2.0015, and 10 to the log 10 cancel out, so we just have little a is equal to 10 to the 2.0015. Or this cell is equal to 10 raised to this cell's value power. So that's little a. To get little b, we'll do the same thing. So this is equal to 10 to this cell's value. Hit the go button, and we have a proposed initial value and B value, or base value. If we look at both of these, we can ask ourselves, does this make sense based on our knowledge of the subject matter? Move that graph back down here. Based on the knowledge of the subject matter, we're trying to get an exponential model for this. It looks like it's definitely increasing, which would mean the B value, our base, should definitely be greater than 1, and indeed it is. And it looks like that initial value, where it crosses the y-axis, is about 100, which is the case. Okay, so this looks like a pretty decent model. So our transformed model is going to be equal to little a, which is in cell G9, times little b, which is in cell I9, raised to the x power. Here the x power, it's going to be, again, this is for our transformed model, so that's going to be our transformed x value. We carry that on down, and we can check to make sure that these model values roughly replicate our y values over here, and indeed they do. So I'll come back to this transformed model, and we'll add that the transformed graph, and add that transformed model to it with the transformed x values and our model values for the y values. Hit the go button, and we see those orange dots appear with the blue dots up here, and they are going relatively straight through those blue dots. Again, let's say we don't think that's the best model for our data. That doesn't model the trend that we know our data to have, or let's say we know that A value should be 100 exactly, not 100.34, or we know what the percent change is, and thus we know what B is. Either way, we can make those changes down here and see the effects on the curve. First off, I'm going to try to bevel this curve out a little bit more, make it more of a cup shaped, basically not taking into account this third blue dot as much. In order to bevel that out, make it more of a cup, we need to change that B value. So instead of a B value close to 1, I'm going to make this further from 1, so 0.045 for that little B value. You could change big B if you needed to as well. In this case, I'm just going to deal straight with the little b value. And it did cup things out, but it also raised those values. So now I need to drop this down in order to make it go more through those blue dots. Okay? And we can keep changing this as much as we'd like in order to hopefully get a better and better model for that data. Here we've got orange dots that start down below the blue dots and end above the blue dots. And maybe that's what we think the best model is. Okay? This is where your knowledge of the subject matter comes into play. You can keep playing with these 4 values here and see those changes live on the graph in an ability to try to get a better and better model using your knowledge of the subject matter. The last step is we weren't trying to come up with a graph for our transformed model. We're trying to come up with a graph for our original data. So let me get some space here. And what we've done is we've come up with a graph not for x and y, but for x minus 25 and y. So y equals our a value, let's say we settled on 95, times the b value of 1.05 raised, and then this is, instead of the x value, this is the x minus 25 exponent. Okay. So our actual model that we'll type in for the original data will be 95, or you could just recall this cell, either way, times 1.05, or we can recall that cell, to the x minus 25 power. So we'll move this out of the way, the transformed data, and put everything back here with the original. values. So our new exponential, I'm just going to retype what we've got down there boxed. So that's 95 times 1.05 raised to the original x values, x minus 25 power. Okay. And you can see that up here, what's been plugged in. Again, if you wanted to recall little a cell, the G9, and little b and I9, you're welcome to. That way you can continue to play with the numbers and see where they end up. But this is going to be our exponential model with the original data in mind. So I'll go ahead and plug it in here. We'll add our exponential model series with the original x values and our exponential model y values. Hit the go button a couple times, and it's a little harder to see because they're gray dots. Let me change the color, but it's a little bit better. But now we can see those exponential points going roughly through those original data values. We can go back here, select the data, and add in that linear model in order to see both our yellow and orange dots. The yellow dots being the exponential model that we settled on to model that original data, and the orange dots being the linear model that we settled on to model that original data. As usual, if you have any questions, please let me know.